Hello.
All right, are we starting to see Macedonia? Officially Western Macedonia, I guess, right? Is that what you go by?
Yes, exactly.
Yes.
Hello.
Hello.
Yeah, I think someone said Macedonia, so I apologize if I've dropped the Western. I don't know. I was going to ask if you have your old team, but shoot, you got everybody all together. You guys are the first one. Everybody else was all separated out, but you got your mask on, so.
Yeah, well.
We tried for the best. Yeah.
We've tested for COVID-19. We were all negative, so yeah.
So yeah.
Okay. Are you ready to go? Are we?
Oh,
Yeah.
we're more than ready to go.
Yeah.
More than ready to go. Okay. All right. Well, here's your first question. So the overall design of your rocket contains multiple complex electronic systems. How did the team determine that all the electronic systems would successfully function simultaneously and were mutually compatible under actual flight conditions, particular EMI, EMC, system testing, or other concerns?
Okay, well, I'm gonna answer this question. I'm Marcos de la Portas from the avionics sub-team leader. Well, the avionics subsystem is actually powered through multiple batteries to ensure that we will never lose the power during the flight. So we are able to communicate with the rocket and do multiple things simultaneously, while also being able to determine whether something has gone wrong or not, and do actions based on that. In greater detail, we actually have thought about about every little detail I'd like to think that can actually go wrong, and do actions, and have actually developed mechanisms in order to avoid and bring the rocket safely back to the ground.
Okay, and is there particular testing that you've done to confirm that your designs really are going to work as intended?
Yes, actually, we have tested the recovery subsystem, and we have ensured that there is a backup for that, because there actually has to be a way for the parachutes to go out and bring the rocket safely. We have done testing for the pressure sensor. We've done tests about the subsystems that collect all the metrics we monitor in the flight, say longitude, latitude, and things about that help us to monitor the behavior of the rocket at any given moment.
And were these done independently, or are they done at a system level?
Well, we've done them independently, but we plan on doing them on a system level as soon as we build the whole subsystem as a whole.
There was a problem with getting some components in Greece because of COVID, and that's why we haven't been able to test the whole thing at the system level yet.
Okay, but you clearly have plans to do that, correct?
Oh,
Yes.
yeah. Oh, yeah.
Say yes, yeah.
Yeah,
okay, very good. Okay, let's see, next question. How did the team conduct reliability testing on the spring-loaded mechanical drogue release mechanism under the variety of anticipated flight conditions, and how did you test under the dynamic conditions?
Yeah, okay. Hi, I'm part of the recovery subteam. Okay, so first we calculated the power that the springs would require to push the nose to eject the nose cone. Okay, then we calculate the dynamic pressure, the nose cone. The dynamic pressure of the nose cone at the speed of the ejection by calculating the speed of the rocket at that moment. And basically we added these two forces, and let's say we wanted to eject the nose cone 1.5 meters up, and we calculate that, and we how do you say, we and we added, yes, and we add the force to the static of the dynamic pressure to that. So yes.
Actually, in order for me to add to that from an avionics standpoint, we developed we added some photoresistors in order to determine whether the nose cone has been opened or not, and therefore whether or not the drogue has been deployed or not. At the moment we need to deploy the main parachute, we have actually developed a mechanism that actually we see whether or not the speed of the rocket at that moment is what the speed should be actually, and we do actions based on that.
Okay, did and just, I may have missed it, but one of the issues is also the spin dynamics. I mean, you're looking at forces due to propulsion, but your vehicle is also spinning. So some additional forces due to the spin dynamics, is that included in your calculations?
Do you want to?
The spin, so
This spinning?
No,
Yes, okay,
actually,
the spinning.
all right.
Yeah.
Actually, hi, I'm gonna answer that. My name is Michael Lazos. I'm the construction leader. And actually, when we studied the rocket flight dynamics, we saw that on apogee, we calculate that the rocket will not be spinning. So the plan there wasn't an analysis that will show that with spin, the nose cone will open, because we calculated to be steady during the apogee, that it's the time that the nose cone will be released.
And wait, can I add something?
Yes.
Yes, and the spinning won't affect the force of the springs, exactly, because
it was overloaded with power to overrule,
Overcompensate.
To overcompensate.
for the dynamic pressure, some spinning if there is.
Okay, so so I think I heard you say that you're thinking that the spin will not affect the spring forces. Obviously, the springs aren't going to be affected, but aren't you going to have any kind of potential, say, interference between surfaces that are spinning due to centrifugal forces?
Okay. The springs are attached on the upper recovery ring. There's 16 springs. And actually, there is...
Can I add to this?
Yes.
I will add to this, sorry. Because the spring system and the pellets that will be eject the nose is very compact to the recovery ring, and they are not in the centrifugal force is not interacting with the force that will eject the nose. So yes, because of the nature of the mechanism, it doesn't impel to that, interfere to that.
And I guess I think I also heard you many times use this thing that you have done calculations, but have you done any actual testing or have plans before you fly?
Labs,
any
of
kind of lab
course.
testing?
Yes.
We're in the process that we await for the whole parts to come to our office to make.
So we got the springs, we got the recovery ring, and we're missing only a few pieces so we can actually
assemble the whole recovery.
Compress the rings. So,
but to be honest, the whole calculations was conducted with a safety factor greater than what was necessary, greater than 2 or 3. So we are more than confident that there will be not any problems in the whole procedure.
Yeah, if I may add to this, we actually anticipated that not everything would be able to arrive. So that's the reasoning behind that.
Exactly.
That large.
But with the collaboration with our teachers in the university and some manufacturers that we know, we have many opinions that this will go pretty well, actually. So again, we're very optimistic. Yes, I'm sorry.
Okay, that's a good, fair answer. So here's a more generic question. If I told you that your mission flew, but it failed, what would you expect to be the most likely cause of that failure? And based on that expectation, what have you specifically done to try to address it and minimize that failure option?
Well, we can. There is a lot of ways to adjust. We can go with a motor. Excuse
me, I didn't hear. It flew, or it? I mean, it was a problem on the after the apogee or before the apogee.
Yes.
I'll leave it up to you. I'll just say,
Okay.
you got off the rail. It looked like it was flying, and then something happened before you hit the
All
ground.
right. I think we cannot.
Approach.
It's kind of a question of like, what keeps you up at night? What keeps you awake at 3 in the morning and you're going, wow, I worry about this.
If we approach the problems from the structural department, we can see a problem that would be that the assembly will fall apart because of the connections. But that's also we've done study for that, and we're pretty sure that will not happen.
Depending on the propulsion sub-team, I guess that a possible problem would be that due to the fact that we were not able to fill the static test, maybe the structure in conjunction with the propellant will show a damage, but we're pretty sure that from our studies and softwares that this will not occur.
And from an avionics point, probably telemetry is what keeps us up at night.
Exactly.
Because it's at speeds that we cannot anticipate what's going to happen.
Exactly.
And for the recovery team, I think it's mainly the drogue's deployment, because if the drogue doesn't deploy, our main parachute can deploy because it will pull the main parachute out of its deployment bag. So if something goes wrong there, it will be a problem. But we think with sufficient testing, it can be minimized. I mean, yeah. We can
That's a
minimize
good
the risk.
example. Like for the payload deployment, one of the things probably I assume you did is to build in redundancy. Right, you have a redundant system so that if the first payload or if the first chute doesn't open, the redundant system would cause it. So that's the sort of thing where you're trying to plan to correct things.
Yeah.
So,
We
do you have a redundant
Yeah,
system?
actually,
Yeah.
we actually can handle those situations programmatically, and if we see the parachute hasn't been deployed yet, we actually check every 5 seconds whether or not the parachute has been deployed based on what I described earlier. Photo sensors and the speed. Every 5 seconds we check that, and we send a charge for the deployment system to open if it hasn't been opened yet. From exactly, in order to do redundancy. But from an avionics standpoint, the failure point is the telemetry, because if we lose the monitor of the flight, we're in a bad situation. So we've actually added the antenna at one fin of a rocket in order for us to minimize noise and to ensure good telemetry, because we actually use an Nesrad avionics subsystem which has its own telemetry
As a backup.
Yeah.
Okay. All right. Go
Excuse
ahead.
If I might add something from the aerodynamic standpoint, my name is Sotiris and I was the aerodynamic engineer. So generally, we don't expect to have we have designed a generally stable rocket, but what we can expect to a problem that might occur would be if our aerodynamic surfaces were not able to provide the stability and the lift that we have designed them to. So this could happen by, for example, maybe the fins, something could hit the fins and maybe damage them, maybe something from the ground. So if that were to happen and this external factor were to damage the aerodynamic surfaces, then, well, this would be a really unfortunate event. But I think that it is really not a great possibility of that happening. And so I think that the rocket would be able to handle the flight with the stability that it was designed to.
Okay, so have you done then structural analysis of your fins, both your fin connection and things such as fin flutter?
Yes, I can answer that. Of course, we've done many analysis on all the parts of the structural, and also in the parts that connects the fins with the inner skeleton to ensure the stability. And we have positive analysis results. Yes.
Yeah, and if I might add, also we have also conducted a flutter analysis for the fins. This is a common point of failure for many launches, and we understand how important it is. And therefore, we have taken steps to eliminate this possibility by conducting calculations. And we found that actually the flutter speed for the fins was really much higher than the maximum speed reached from our rocket. So we again are really confident on our decisions there from the fluttering standpoint as well. Yeah, we took great care in ensuring that the flight would be safe, number first, and then reach the apogee as well.
Very good. All right. Well, I appreciate that. So Steve, Chris, you guys have any follow-ups? I think we're about out of time, but we could jump in. We're good. Well, we appreciate it. I think I'm not, you guys are 7 or 8 o'clock at night or something, aren't you? A whole different time.
It's 10:30,
Yeah, okay. A whole other part of the world. So I appreciate your willing to accommodate all the times.
It's a great honor for us
competition
for this competition. So
Thank you.
Thank you so much.
Thank you so much.
We enjoyed your report, and we enjoyed chatting with you both here and in the earlier presentation. So thank you very much.
Oh, thank you.
Thank you very much.
Thank you very much.
Thank you very much.
Look forward to seeing you out in the field next year, and we'll be flying, right?
Yeah, we
We're
hope so.
We're hoping for the best.
All right. Take care. Thanks again.
Thank you.
Have a nice-
Goodbye.
Bye.
Bye.